We're a software consultancy. We were one of the early adopters in Elixir, and we have part of our business model and our path to our success is ensuring that the Elixir ecosystem is firing on all cylinders, basically. So we want to invest in it. We make heavy investments in it. We hired Chris to work on Phoenix full-time, well, mostly full-time. He does a little bit of billable work, but that's primarily to work with clients on features that he's developing for Phoenix. We hired Paul to work on releases last year, and over the past 6 months or so, we've been working on something new that we're proud to share with you today. And it is called Lumen. So, see if this is working yet, because I like to wander, but I'm going to keep finding my way back. Bear with me 1 second, because I would just plug in the other dongle. I can get it working. Okay, good. All right. So, what is Lumen? Lumen is Elixir plus WebAssembly. Last year's conference, part of my Dockyard sponsor Keynote, I used that opportunity to address all of you on our desire to pursue this as a company. And I put it out there saying that this is what we want to do, this is something we want to invest in, we have our reasons for doing it. And most people came up to me afterwards and said, like, why? Why would you want to do that? We'll be addressing some of that later on in the talk. But just know that this has been in my head for quite some time. On the ElixirLang Google group, back in 2016, March 23rd to be exact, I actually posed the question to the core list. WebAssembly was very much in its infancy there, under tons and tons of feature flags for the browsers. But I was fed up enough with JavaScript. I was looking for some sort of exit hash as soon as I could get. But I didn't want something that was simply just a transpiler. That wasn't very interesting to me. But apparently it wasn't interesting to anyone else because it took me waiting an entire year. If you look down at the next message, which was a year later, I brought it up again, and that's when I started to get a little bit of response. Jose and I had some conversations around it, and it started to really evolve from there. The decision at the time, in my head at least, was to wait for WebAssembly to mature to a certain degree. And about a year ago, it reached its 1.0 status. At that point, I decided this was something that, as a company, we can start to invest some serious money into. So over the course of the next 45 minutes or so, we're going to be going over what we've accomplished so far, what we still hope to do, and hopefully we can get everyone interested to really participate and help make this something really awesome. So I'm going to hand the mic and I guess this over to Paul to speak about the compiler.
Yeah, I am going to talk to you a little bit about how we're actually compiling Elixir for WebAssembly. One of the things that we wanted to avoid doing was just basically tacking Elixir syntax on JavaScript. So this is not that. The goal is to essentially bring the beam with Elixir on top of it into the browser. So that means processes, supervisors, all the good stuff, but running on WebAssembly in the browser. So there's a few things about actually doing that that I want to talk about first before I get too deep into the compiler. There's some interesting constraints about building for the web, especially for the Beam, about WebAssembly itself, and details about actually interoperating with JavaScript APIs in the DOM. As far as constraints go, the main ones are code size, load time, and just the way that concurrency is implemented and how threading is implemented. Code size is a major deal in the browser, right? So the larger the amount of code you have to ship to the browser, longer time the page takes to load, and it starts to impact like user experience pretty quickly. And shipping like large amounts of bytecode is a major factor in that. Load time, just in general, how fast it takes to immediately start executing useful code is important. As far as the concurrency model goes, threading in the browser is implemented with web workers currently, and it's a very different model than it is, say, for POSIX threads. It's essentially more like OS processes in nature, very isolated from each other. Although some of that's changed with like shared array buffer, which allows sharing memory between workers. But that's basically disabled by default in most of the browsers. I think it might have been re-enabled in Chrome, but not in Firefox. WebAssembly specifically is sort of an interesting architecture. It's what's known as a Harvard architecture where code and data are actually separate. So if you think about code for like x86, code and data live in the same memory address space. So you can take the address of some code, say the address of a function, and jump to that code and start executing it. In WebAssembly, you can't do that. So the equivalent of like a function pointer is actually an index into a table of functions, and then the WebAssembly runtime knows how to actually execute that function based on an ID. So all the instructions in WebAssembly are based on indices like that, not real addresses. It does have what's called linear memory, which is essentially equivalent to regular heap memory. But that also doesn't use like actual pointers, it uses like integer indices. Sort of like a big array, if you think of it that way. It works also using structured control flow versus arbitrary control flow graphs. So the difference there is that control flow graph allows multiple entry points into the same block of code. So if you think about a loop in like C on x86, you can write like a goto in the middle of a loop. That is not permitted in WebAssembly at all. Everything has to have a single entry point, so you don't have arbitrary gotos, for example. And then as far as the barrier between JavaScript code and WebAssembly code, currently, this is changing, but the current state of the world is that you can only pass integer values across that barrier. So that's obviously very restricted in terms of what you can do with that. Essentially, the only way to pass objects in and out is to convert them by sharing a pointer into the linear memory of the WebAssembly module and parsing what's in that memory. So this has an impact with interop with the JS and DOM APIs. So FFI is heavily impacted by the fact that you can't just pass arbitrary values across that barrier. In particular, you basically have to have translation routines written in both the WebAssembly side and the JavaScript side in order to do translation. Async functions are a little bit unique, particularly with the Beam, in that you have to pass a callback, but that callback has an arbitrary lifetime, so you don't know when to garbage collect it. So there has to be some extra like boilerplate code that knows how to basically garbage collect those things, know when it's done being used. And then events, when you're just writing JavaScript code, it kind of manages all that for you, but with the Beam, we need some extra like subscription management and dispatch code that can handle receiving an event and then translating that into like a message to a process. So we basically took the approach of building a new compiler versus porting the Beam to WebAssembly for a number of reasons. The easiest of those is really just that the runtime requires a significant amount of work to port over to be compatible with WebAssembly. And then code size of the bytecode itself is extremely large, impractical really for any sort of real production use. And then there are some performance things about running a virtual machine on top of a virtual machine. Because if you think about like the WebAssembly runtime, it's a JS engine. So you're able to like just-in-time compile some things to machine code if it's able to recognize and optimize those things. But then you're layering on top another virtual machine. So you have like an extra layer of indirection for everything you do. And that has performance implications. So as far as the runtime is concerned, the main thing is that a lot of APIs that the Beam is built on top of just don't exist at all in the browser. There are some ways to work around that, like within scripting. It will tack in like a libc that's been like manually ported to JavaScript. That allows you to access some things, but a lot of those APIs don't really work the way you would expect them to. The bigger issue is that the scheduler itself is written as in two major ways. So the threading model that I mentioned with WebAssembly, you have like a main thread and then these web workers, and the model in which those things work is very different. The main thread has the shared processing time with the UI. So that means any blocking CPU consuming work you do on the main thread impacts the way that the UI renders. So it can get really jittery really fast if you're doing too much work on the main thread. Web workers can't access the DOM except for communicating with the main thread to do it for them, but they don't have to interrupt or like yield any processing time for the UI. So there's a little bit of a split in role there, where the Beam scheduler assumes that all of the scheduler threads are identical in nature. So once it boots up into that main scheduler thread and forks off the other threads, they're all essentially identical with each other. So in that sense, the scheduler needs to be reworked to basically understand that split and role and be able to support that. And with the main thread in particular, that means the scheduler has to know how to yield back to the JavaScript engine. And that's just fundamentally not part of how that scheduler works today. These are things that could be addressed, but would be a non-trivial amount of work. And then on top of that, there's the way you interact with JavaScript values. So one of the things that we found was that we needed a new type tag. So if you think about the term scheme in Elixir and Erlang, there's all these different types of terms that each have what's called a type tag that identifies them. We needed a new one specifically for JavaScript values because they're actually garbage collected by the JS runtime, not by us, which means that they have to be tracked differently. There's essentially like an opaque reference. You can think of it as like a pointer, but it's not a pointer. And so the runtime needs to understand this new type, and that touches all kinds of code throughout the Beam code base. Like I mentioned with code size, like shipping the Beam bytecode is very large. I actually did some measurements just compiling one library, wrote timex, just the Beams for timex. None of the standard library, none of the Erlang standard library. And without stripping them, they were 1.1 megabytes in size, just the Beams. With them being stripped, it was down to 500K. But if you imagine like the typical application has several of these applications, and you have to ship the entire standard library with you pretty much as well. So that very quickly gets into like the 10 megabyte range or higher, depending on how well it's able to strip the Beams. It might be smaller than that, but it's way too large for the web. Mobile devices in particular are going to suffer if they have to load 10 megabytes of just bytecode. And that doesn't count compiling the runtime itself to WebAssembly. And one of the reasons why we have to ship so much bytecode is because Beam just has very weak dead code elimination. If you're not familiar with the term, it's also called tree shake in the JS community. Basically identifying code that's never going to be used and stripping it out entirely, not shipping it. For a variety of reasons, the Beam is not able to really do this too well, except for in like local contexts. The main reason being that you have hot code reloading, which means that at any point you may need to call new functions. And the other part is like the apply function call that allows you to dynamically construct a call to anything. Both those things essentially mean that you have to assume that anything in the dependency graph of an application might be reachable at some point. And like I mentioned with performance, running a virtual machine on a virtual machine is not ideal. If the JavaScript engine is able to JIT some of it, it might be able to avoid some of that overhead. But we wanted to essentially avoid as much overhead as possible, both in terms of space and time. In particular, the JavaScript engine is really not able to reason about the beam bytecode like at all. Basically, the only part it would be able to optimize would be the core scheduler loop and maybe some of the runtime functions. So the approach I chose was to build this as a new compiler. So I wanted to think about like how would we do this from the ground up, try and solve some of these problems. And the solution that I kind of arrived at was like if we impose some restrictions and approach this as an ahead of time compiler instead of a virtual machine, we can probably heavily optimize that code, strip out a lot of things that aren't needed at runtime, make the package much smaller and more efficient. And if we take advantage of some open source tooling, particularly tooling around WebAssembly, we can probably hit the ground running fairly quickly. So specifically with regard to restrictions, what I mean is getting rid of the idea of hot code loading. It's not particularly a thing that we really need in practice in browsers. It might be something that could potentially be added down the road as like a JIT thing, but I wanted to make that a restriction up front because I don't think it's used in practice very often anyways and didn't seem like a good fit for this use case. And then loosening the restrictions around dead code elimination to allow it to strip out code that can't be statically resolved as reachable. And what that means is if you have like an apply3 call that constructs a call at runtime, the code that it calls, if something else didn't need that, it might not be there at runtime. But then add some functionality to allow you to say, like, definitely don't strip this out. So the benefit there, and combined with like the ahead of time approach, means that you're only really paying for what you use at runtime. Instead of having to ship all the code that you might need, you only ship what you actually do need. You avoid the interpretation overhead. The WebAssembly runtime is able to reason about the code much better, optimize that better. And in general, the ahead of time approach means that we can run a lot more static analysis and do much more optimizations than we would be if we have to assume that the world can shift under our feet. That's the major issue with hot code reloading, is that it's very difficult to do optimizations, whole program optimizations, if you don't actually know that that's static, that code's static. And then in general, we can do target-specific optimizations when we compile for a target that you can't really necessarily do if it's run dynamically. And the existing tools that we decided to build on are LLVM for the compiler itself, because it has a WebAssembly backend that's seeing a lot of attention from a variety of parties. Google and Firefox in particular have members working on this. The compiler itself and the runtime are built using Rust because it has very good WebAssembly tooling currently, and that's a major effort in that ecosystem. In particular, the WASM bindgen crate that has a lot of really convenient tooling for generating bindings to browser APIs, JavaScript APIs. So we're taking heavy advantage of all those. The compiler itself has some like key challenges that it really needs to have a solution for when compiling ahead of time. So that's recursion and tail call optimization. Erlang has no like loop while concept, like no for keywords. So it depends entirely on recursion to do any sort of iteration or traversal. And that means that it's heavily reliant on tail call optimization to avoid blowing the stack. Non-local returns and exceptions are very cheap in Erlang. So that means if you use throw, you can jump out of some code to some other area above it in the call stack, and it's not imposing a lot of overhead. There are some costs, but it's relatively cheaper than, say, like C++ exceptions or something. And then also the implementation of green threading. That's processes, right? The actors themselves. They appear to be preemptively scheduled. Under the covers, it's actually cooperative scheduling, but implementing this in a way that works with native code is much trickier than with a virtual machine. So these were three major pieces to the puzzle that I needed a solution for. And then WebAssembly specifically has some challenges, namely that its abstract machine, the model into which it's designed, is stack-based as opposed to register-based, like pretty much every other target. The beam itself is a register machine, not a stack machine. The fact that it requires structured control flow, which limits how you can implement some of the features I was just talking about, like non-local returns. And likewise, no direct access to the stack because code and data are separate, and WebAssembly also hides the native stack, also restricts options for implementing that. And so I needed a way to solve these problems while compiling ahead of time and for native. And the solution to that is called continuations. I don't know if you're familiar with this at all, but I will tell you real quick what they are. Basically, you represent what are traditionally jumps, like if you're branching and jumping to a block of code. Normally, that's like implemented with a jump-like instruction. And with continuations, they're structured like function calls. And all of these calls, like the code is transformed, so all these calls are in tail position, which means that you're relying on tail call optimization. The continuations themselves never return, so the program's always advancing forward. It never like jumps back up the call stack. And continuations are strictly like a superset of all control flow mechanisms. So it can be used to implement all kinds of cool features like exceptions, green threads, et cetera. To give you a quick idea of what that looks like, this is like a very small, simple, naive scheduler thing written in Elixir syntax, and with the continuations made explicit. So that K parameter on like the fork and yield functions here is the continuation, and you can think of it like a closure or a function being passed in as an argument. So like the fork one takes the continuation, queues it, and then calls the function. And the yield one enqueues the current continuation, dequeues the next task, and calls that task. And then like the loop function here is just, the control flow has been inverted to use continuation. So the yield part here is passing in the rest of the function as a continuation. And so the spawn proc one just spawns a new loop that's got a counter at 10, and it will decrement each loop that it makes. And then start function just starts two processes that each pass in, like it's written in continuation passing style, so it might be a little bit confusing, but you can see what happens when you call that start function. It basically switches back and forth between the A and B processes until they both reach the count of 0. The way this model works is it essentially inverts the control flow so that the rest of the computation of the program is like reified as a closure, a function that you can call. And then that can be stored somewhere and then fetched later and called and jump straight into that code. So that's how continuations work, but the continuation passing style model is hidden from you. So you don't have to write code like this. The compiler generates it for you. And so real quick, I'll touch on the compiler architecture, almost done here. Our front end takes in both Erlang source files and Core Erlang source files, and we have like a mixed task that compiles Elixir source into these, into Erlang or Core. The reason for that right now is that we didn't have the compiler hooks necessary in Elixir to kind of like directly call the Lumen compiler from Elixir source, but that's something that I plan to address in the future. One nice thing that we get from this is that we have much richer diagnostics than currently exists in the Erlang compiler, so it's able to show you the source snippet where an error happened and like annotate it in different ways. If you've seen like Elm error messages or Rust error messages, they look like that. Our middle tier lowers the abstract syntax tree from like the Erlang source or core to what's called EIR, or Erlang Intermediate Representation. And this is the stage at which we do like semantic analysis and everything. EIR is based on research IR called Thorin, which is graph-based IR, not an SSA-based IR. The main difference there is that it allows a much broader set of optimizations to be performed than are possible with just SSA, or if you're familiar with continuation passing style. So it actually is kind of a CPS-like IR, but is quite different. It doesn't have some of the disadvantages. In particular, it doesn't require like creating closures for all those jumps. It's able to convert those into actual jumps. And then we have an easy way to transform that into SSA. LLVM IR, the backend CodeGen IR, is SSA form. And so we have an easy way to transform it from EIR to LLVM IR. And then this is in EIRs where we do all the high-level optimizations, like pattern match compilation, for example. And then the backend just takes EIR, lowers it to LLVM IR, does linking and CodeGen. So that's where we get like the object files that we link together, or that can be used as a library, or generates an executable. In the case of the WebAssembly target, that means we're generating a .wasm file. So future goals is we need a lot more metadata in LLVM IR to do better optimization. So one of the things that we would be able to do with this, for example, is lower type information down so that it can use like the math intrinsics at the platform level, be able to do like auto vectorization of loops and things like that. We want to be able to target embedded, and I am also interested in bootstrapping the compilers so that the compiler itself is also written in Erlang and Elixir. This would be key to getting community contributions rather than having to learn Rust to be able to contribute. And then there's a new library called MLIR. It sits on top of LLVM IR and is currently used by like the TensorFlow framework as a new CodeGen backend. I would like to take advantage of this so that code that has enough type information could be lowered down and actually be able to generate really efficient loops and like tensor multi-dimensional array code. So if you're doing anything that's like graphic rendering or machine learning, things like that, would be able to take advantage of that. That's it. I tried to pack in as much as I could. I got to hand it off to Luke now, but if you have any questions, definitely ask me later.
Hello, I am Luke Imhoff, and I am a software entomologist. I research bugs. So, you may know me around the internet as Chronic Death. I also maintain the IntelliJ Elixir plugin. The runtime is composed of 5 layers: memory management, terms, processes, schedulers, and BIFs. The first layer is memory management. The memory management layer of the runtime was a collaborative effort between Paul and myself, as he talked about. Paul thoroughly studied how the Beam does memory management and the current best techniques from the Rust community. So our allocator is very close to how Beam does memory allocation with chunking, so it's very efficient to create and free processes, and that they're sized to what's normal for an Erlang or an Elixir process. I thoroughly tested that implementation with the prop test we have for the BIFs, ensuring that you are safe from seg faults. And this isn't me just saying like, they passed, we prevented seg faults. I mean, I found seg faults and I fixed them. There are no seg faults. Adaptations had to be made from the Beam implementations because some of the techniques, like asking for but not using memory, a lot of the VM syscalls just do not work in WebAssembly, like Paul mentioned. From the Erlang and Elixir program perspective, the memory model, though, is the same as the Beam. Each process is a separate heap, and binaries over 64 bytes are reference counted. Paul made sure that the process heaps use the same heap size algorithm. Garbage collection is still per process. On 32-bit systems, we mostly follow the bit pattern used in the Beam, which you can read about in the Beam Wisdom site or the Beam book, which are both great. On 64-bit systems, Paul made the observation that x86-64 is only designed to address 48 of those bits currently. Like Intel says Yeah, it's a 64-bit CPU. You can only address 48 bits of memory. They have slowly, with newer chips, been increasing the bit count, but you are not actually able to access 64 bits of memory. And because of that, we have free bits to use, which means that on 64-bit systems, we can put all our tags in the high bits, and unlike on 32-bit, we don't have to shift every time we want to get a integer out of a small integer term. So it's much more efficient. Because we're ahead of time compiled, we don't need all the terms in the beam, and so we repurpose those bit patterns to simplify what Beams calls a magic ref, which are references to resources and NIFs, and instead we call those resource refs, and that's how we're interacting with the DOM APIs, as Paul mentioned. The processes have similar features to those in the Beam, and from early Elixir code, they behave identically. Like in many native processes, memory is used for both heap allocations, which we put at the start of the memory, and stack allocations, which are pushed to the end of process memory. The heap and the stack grow inward towards each other. When they collide, GC is triggered. The code stack keeps track of the module functionalities used for Erlang and Elixir backtraces. We need to keep track of this separate from the native call stack, which can be heavily optimized due to inlining that the Rust compiler and LLVM can do. The mailbox supports both messages stored in the heap and off-heap messages similar to Beam's approach. If the processes you're sending to isn't your current process and you can't acquire a lock in the process heap, we make an off-heap message, and then we put it in the process off-heap, which is a faster lock. This is how Beam works under the covers. The built-in local name registry, but not the Elixir capital R registry, is also built into the runtime, the same as on OTP. Lumen schedulers work similar to Beam schedulers in that there is one per thread. Each time the scheduler runs, it checks if any of the timers need to time out, but only runs one process. How the schedulers work differs for WebAssembly target versus a native target, though. On the web, the first scheduler is started on the main thread of the page, and any additional threads have to be started as web workers, as Paul mentioned. On native, so x86, 64, ARM, embedded, anything really Rust and LLVM can target this point. There are no special threads. From the testing, we know that the more schedules, then the number of cores can run just fine because Rust test framework spawns up a new thread for every test, and we have over 3,000 tests, so over the course of our test run, we spawn 3,000 schedulers. WebAssembly calls are blocking. There's no built-in support for declaring a function as async the way there is in JavaScript now. Even if we could declare an async wrapper, we want the timers to work without polling and without hoping an event lister callback are called and enters back into the WASM module and wakes it back up. We want your code to be responsive and act the way you expect it to act and not have weird lagginess. The WebAssembly specification that says when a WebAssembly module is instantiate, a function named start, export from the module is called. If you're used to like Windows programming, this would be like your DLL main or your entry point in a shared object in Linux. For Lumen's WebAssembly target, we redirect any Rust level panics to the JS console so that if the runtime we're giving you ever blows up, you have a bug to report to us. We are actually using that for sections that we don't have done. We use the unimplement macro so that you'll know instantly to tell us, hey, I need this feature that you didn't implement yet, please implement. And that's from the community feedback, we'll know where to focus our efforts. We register a function that allows us to map module function arities past to apply3 and spawn to compiled code. This is for the stuff where we can't make it an exact call and we have to do a dispatch using atoms. With the compiler, though, most of the time we will be able to eliminate those. And finally, we start the scheduler loop in Lumen Web. The loop is not an infinite loop statement in Rust, but instead is a function that reschedules itself with request animation frame. On each frame, we run for what we expect to be the frame number of milliseconds. How long that is can vary based on the refresh rate. That's like the definition that MDM gives you. But we're assuming 60 frames per second because that's what they say you have to expect. But if you think about that, that also means that we only get scheduled every 16 milliseconds. So it's a simple loop where we keep scheduling until the monotonic time exceeds that 16 milliseconds. So it's very similar to games programming where we have a frame to do everything. The while loop can exit early if there are no processes to run, such as if all of them are waiting in a receive block, or there are no processes because no calls have come in from the JavaScript event loop. So from doing this, I learned a lot about JavaScript and that the web browsers have a very specified thing of when different parts of JavaScript code and WebAssembly code get notified of stuff because there's an event loop and a microqueue task for async stuff. So it's very specified when it will actually notice. And if we don't yield control, some of our demos would be doing all the work, but because it was stuck in WASM, all the data would pop on screen after like 10 seconds. It's very jarring. For our test demos, the tab idles at 3 to 4% CPU because of the spin loop. We plan to further optimize the loop by finishing the frame early if there are no timers that will be due in the rest of the frame. So we can look ahead because we use timer wheels to do that. When the scheduler is run once, it services all timers but only one process. The timer wheel hierarchy is modeled on that used in the Beam with an at-once slot, a soon and later wheel composed of multiple slots, and a long-term slot. When the scheduler checks for timer timeouts, it also advances the timers that are closer to timing out up the chain. Due to the fallout from Spectre, even performance timers like performance.now in web browsers only expose a native resolution of milliseconds. For consistency, the Lumen runtime treats milliseconds as the native resolutions instead of microseconds the way Beam does. At first, I was going to go with 32-bit unsigned integers for mod time, but that is only 49 days, and I feel like I keep tabs open longer than that sometimes. Plus, it means you couldn't use a send after for a once-a-year calendar notification when you use Lumen to replace Google Calendar. So instead, I went with 64-bit, which is a bit better at greater than half a billion years. When we try to dequeue a process from the run queue, there can be one available to run now. The next process has a low priority, so it is delayed and we check again. Or there's no process to run, such as when they're already in a receive block. We actually signal this back, and that's how we're exiting the scheduler loop early. When there is a process to run now, though, we first check if the process is exiting. The process can be exiting already because another process could have told it to exit with an explicit like exit or kill call, or through a link process is exiting, because when a process exits, we don't want to go down the entire chain because that would take a long time. We want to propagate one level and then let that process get queued to see if it exits or just traps it into a message. When the process is run, we drop into code derived from your Elixir or Erlang source, and when it returns, we check if it needs GC. If the process was already exiting before we tried to run it, or it started exiting due to a runtime exception in the Lumen compiled Elixir or Erlang, then it will fail to requeue and it will exit. When a process exits, we log that it is exiting using the ** exit message everyone is used to seeing from proclib processes, which makes it much easier to debug your code. If the exiting process has any links or monitors, it will propagate those exits through link or exit messages through trapped exits or monitors. When the process run code, the base leaves of any call graph are the BIFs or built-in functions. For Lumen, I started by listing out all the functions in the Erlang module, as they are all BIFs, which meant that there were 326 functions to implement with 12 weeks to decide on a go, no go at the end of May when I started on this at the beginning of February. It would have meant making an average of 28 BIFs a week. I'm now able to make a NIF in like an hour, though, so it's now practical. It wasn't at the time, though. After getting through 45 of the BIFs and having the accompany runtime features, because when you first start out, the runtime isn't really there. As you add BIFs, it gets easier and easier. That was the end of March. That is 7 weeks. I realized that the 20 BIFs per week pace wasn't very realistic. I went through and categorized the BIFs by what we need for an MVP. That left 127 BIFs to implement, so the work was cut by more than half. As of today, Lumen Runtime has 126 BIFs defined in Erlang. While implementing those BIFs, I also defined one in binary bin to list because it replaces a deprecated one in Erlang, binary to list 3. Gen server in Elixir uses most of the BIFs in the list module, so all 5 of those are implemented. Supervisor uses merge and is key for maps, so those are in there. There are 11 total in maps. Binary lists and maps are weird in that they are a mix of both BIFs and normal Erlang code. Like when you load a NIF module, you don't necessarily replace all the Erlang code or all the Elixir code. So you can actually have wrappers around your NIFs that are just normal Elixir code, which is sometimes nice. You can have confidence in those BIFs and the runtime features backing them because of the thorough testing in Lumen. Lumen Runtime has over 2,000 tests, with about 90 of them being property tests using Rust prop test library. I still have no idea how to write a property test for a Phoenix app in Elixir, but I'm very well practiced writing properties for BIFs in Rust. It's very much easier to find an invariant for add. The switch from example tests to property tests allowed me to eliminate examples for each different term type, which is necessary to show that if you pass a non-number to add, that you get a runtime exception that your Erlang code can catch instead of a Rust level panic. Using prop tests, we explored a much larger memory space and combination of terms, and we're able to isolate and fix seg faults from nested tuples, lists, and maps. Some of which came from usage of Rust libraries that didn't exactly play nice with the fact that Erlang terms can sometimes be an immediate that's packed into 32 bits or 64 bits, and sometimes it is a pointer, and Rust did not understand that in certain cases. When I switched the tests over to prop tests, the number of tests shrank from 9,890 tests to 1,998 tests with a net deletion of 50,000 lines. If you're thinking of evaluating prop tests in any environment, I would think it is a very good idea. Prop test does not currently work well with WebAssembly because WebAssembly uses because WebAssembly uses the 32-bit tagging scheme, but all the prop tests are testing on the 64-bit tagging scheme, we still need some way to exercise the slight difference in tagging. So to do that, we have WebAssembly only integration tests using our demos, which exercise the full runtime. Currently, we have tests in Chrome and Firefox, but we're blocked on running the Safari driver in the macOS executor on Circle CI. So if you know how to get Safari driver to work on Circle CI or any other CI, please help us so that we can make sure this works in Safari. I will say that Safari and Apple is not as involved as Chrome and Firefox are, but it's supposed to work, so it's probably just us running it wrong. So how do we actually interact with the web? First, we'll cover JS calling Lumen. As I described in the scheduler section, once the WebAssembly module is instantiated, the scheduler is started and runs in the background using request animation frame. So we don't want to make a blocking call into Lumen, so we call a function asynchronously. Once in Lumen, we spawn a process with an executor at the bottom of its stack and return a promise using the executor. The JavaScript keyword await uses that promise and waits for it to resolve or reject. While JavaScript is waiting, the request animation frame loop is running the process. When the process gets to the bottom of it, resolves the promise using that executor. With the promise resolved, on the next microtask in the JavaScript event loop, the await is awoken and returns the resolve value. So let's go into detail on that. To call asynchronously, we use the await keyword in JavaScript. In Lumen generate code, we're doing the equivalent of the following Rust code. Lumen web wait with return 0 spawns a process in a special way where the process is in memory, but it is not scheduled in a scheduler. This allows us to add a frame to call the Elixir code in case the function here, Elixir chain non-arity1. Diving into Lumen web wait with return, it calls spawn unscheduled, which we care about because it's going to generate that JavaScript promise we need for the await keyword. Spawn unscheduled spawns a process, but not in a scheduler yet. Before we return the process for adding the compiled Elixir Erlang codes frame, we create an executor. Convert it to a resource reference, which remember is our special type that we're using instead of the NIF type that Beam would use. And we push it back on the stack so that the code can find it later and fill it in. The code function will need to access the executor so it resolves the promise. An executor is very simple, though. It is a struct that keeps track of whether a promise is pending, resolved, or rejected. To generate the promise, we actually pass it into promise new, our executor, and we only need to record the callback functions. If you're not aware how JavaScript promises work, as I was, you might not realize that this isn't actually something special about Rust promises. It's the way it works the same in JavaScript. This might look more familiar if you've ever turned a timeout into a promise. In this case, the closure is an executor instead of an explicit JS object. Back in JavaScript, chain run 1 returns, but a promise, so await keyword waits. In any given frame of compiled code, we're going to get the arguments from the stack, replace the current frame's code pointer with the next label in the current function. And when I say label here, this is like if you've ever looked at the disassembly Beam bytecode where they have literal labels. and then call the next body recursive function that we want to return to that label. Because we want to always show the current function on this stack trace, we replace the current frame with a continuation label so that it'll always have the module function arity look correctly. We could rearrange it so that we rearrange our code, but the stack frames would be confusing, even though that would allow us to eliminate some labels where you're passing the return of one function directly as the input to the next, like a pipe. But it makes the stack frame confusing, so we didn't go with that. We then push on the function we want to call as a body call so that when it finishes, it pops itself and returns to that label. For tail calls, we merge step 1 and 2, so that the next call replaces the current frame instead of pushing one on top. When the code returns the bottom of the stack frame, we run the wait with return code, which does the resolve. So it is pushing on the return term, the first stack pop, but that executor was already sitting there waiting for us to come back into this code. With the promise resolve function called, the JavaScript event loop will return from the await. Lumen calling JS is treated as NIFs that we implement in the Lumen web created in the repo. We hope in the future to automatically derive all the web APIs using the web IDL that Rust's WebSys crate uses, but for now we are manually wrapping WebSys. Web IDL is actually a standard that, until this work, I did not know exists, that the reason why browser APIs is compatible is there's this description language for the interface called Web IDL, and they all implement that. That's why browsers are compatible now. Currently, all these calls are synchronous and not promises, but if we ever start to use APIs that are slow, we might use promises. So coming in, async, going back out to JS, sync. We have some idea what it can do, so let's actually see it. We're going to skip the fib and go straight to spawn since we're short on time. When I first started learning Elixir, the first book I read was Dave Thomas's Programming Elixir. In that book, to demonstrate the ability of Elixir to spawn far more processes than the number of threads or cores, Dave has an example called spawnchain.ex. This example was the one I would show to Java and Ruby developers to impress upon them how processes can be used whenever something is parallel instead of worrying about thread pools. It can run 1 million processes in about 40 seconds on a fairly old MacBook Pro. This is the spawn chain demo. It is based on the spawn chain in his book. What it's doing is it is going to spawn n processes, then collapse the chain down by taking the last one you made and sending it backwards through that chain to the earlier pit. So it's a very indirect way to do sums, but it demonstrates things very important. It shows that we can spawn 1,000 processes and have them just sit there and wait. We then show that they can be woken back up and send data between them without any memory corruption. So now let's go to the demo. So this one, yeah. That one? Okay. Okay. So here's the demo of spawn chain. Oh, okay. This is slightly more involved than the normal Elixir code because we want to do some interesting things. So let's do the boring thing. Spawn chain run is, we're just going to open up the inspector, and we'll just run it. Make that big. Yeah, there we go. Everyone good? Okay. Okay. We get a promise. Remember, I said it returns promises. So what did I say we have to do? We have to wait. So what do we get back? This is just a quick hack. I didn't want to implement a tuple type, so I just made it return an array. The first thing is the time in microseconds, because this is using the timer TC function that's built in Erlang, and then the count. We always expect n, the count, to work. The reason we do that is, hey, there are bugs sometimes. It's important to know I got it right. So can we go bigger? How many processes can we run? 10? Okay, that was kind of boring. 100, K, 1,000, cool, 10,000. Okay, but you're like, it's just giving me 2 numbers. Is it really doing anything? Yeah, there was a slight delay. Maybe it's just asleep. So let's see what it's actually doing. Let's do the same thing when we're going to log to the console. So here, it's printing the PID of the thing that's doing the work. It's showing the value getting sent and the result coming back. but that's just one. So let's do the big ones. So there you can see all of them are spawned, they're waiting, and then they all collapse back down. I mean, we can go, pretty nuts. 6, 5, 6. So this is 64K. Now, I'm not using web workers here. There is only one thread because, remember, Firefox hasn't enabled shared array buffers. So us using web workers doesn't really have a payoff. So this is all running in one thread. And you're like, oh, it's kind of getting slow. Is the Erlang getting slow? No, part of this is we're still in the browser. There still is a repaint penalty. So if you think about it, we are constantly repainting this section of the console over and over again. We're spitting so fast. So that's in microseconds, remember. So that took a minute. So we're not that much slower than Beam was doing this, and we're doing it in a browser. And remember, when the Beam is fast, it can schedule to all your cores. So this is doing it single thread. So this would be going back to the pre-SMP version of Beam and getting these numbers, which I'm not sure it could do, because we don't have that code anymore. But I mean, that's the console. The reason we want this is we don't want to print console messages. Great, that's developer tools. We want to interact and make our customers see this. So let's see it. So that table was created all in the background. What if we do the big numbers again? What happens? So we do a wait. And I can keep up. That's fine. If I do very large, though, I cannot actually do command down fast enough to keep up with how fast we can print. So right now we have output, but all our inputs are from the console. That's not very interesting. We want inputs from how users interact. So let's interact. So that form has an event listener. That event listener is triggered, it spawns a process, and it does all the work that I was doing from the console. So let's see why that actually works. So how does the form work? Looking at the HTML source, all that is there are two data attributes, data Lumen submit module and data Lumen submit function. Take an example from Phoenix Live Vue.js. Lumen Web Start registers an onSubmit event listener on the window, so like a global event listener. When the event fires, it checks for these data attributes if they exist, and if it does, it runs the module and function. This is a very rough thing. We're not saying this is the final framework. Lumen Web Window onSubmit is handling is a rough first step. I came up with it on Sunday. We want to encourage experimentation. The Lumen team is not sure whether the community will want to have a framework like this. We hope the community will expand on our work. So we see a couple approaches. We could have a support so that you can take your live view templates and live EX and just make them work with Lumen. And all of a sudden, we have an answer to the joke of, what about offline mode? Another approach, of course, would be to adapt a scenic-like approach from Boyd's work, but we want the community to explore this. Hans, myself, and Paul we're back-end developers. We don't know what feels right on the front end, so let us know. You probably care about, you saw the speed, you saw how fast it was, but what are the actual numbers? Lumen on x86-64 is quite fast, taking under 8 seconds natively to do the chain run where we only output the number at the end with no logging. But surprisingly, it's even faster in the browser, taking only 5 seconds there. We'd like to thank Google and Mozilla for spending just loads and loads of money to make WebAssembly and the JIT awesome, because we did not expect this result. Under certain scenarios, the WASM is faster than the beam. We were shocked by this. When we compare the time to run chain and log and do all the sends and receives in the console, it does get slower, as you saw. So instead of taking like 5 seconds, it's taking 8. But most of that is due to the repaint. When we do the log to DOM demo and we don't follow it, it is much faster. So a lot of this overhead is due to repaints. So those repaint overheads are the same overhead you'd have with any infinite scroll thing where you constantly keep the scroll at the bottom. So if you were ever thinking of a very fast output from like a CI server, you'd have the same problem with normal JavaScript. It is not something about Lumen. It is just the overhead browsers have doing repaint. So let's move on to our future work. This is where your help is needed. The BIFs are not yet all implemented, but they fall into 2 broad categories. Those that we're quite sure we'll want and we'll work on immediately, and those that we'll only implement after those are done and maybe never. For the ElixirConf 2019 onwards milestone, the process monitor, number conversion, some of the process spines, so like the weird ones like op3, op4, the ones that take anonymous functions instead of module functionality, those sort of ones aren't done, but actual spline processes works. Process dictionary BIFs are unimplemented, but like the underlying dictionary exists. We just didn't need to call them in the code, so we didn't implement them yet. But they're very simple writing BIF-style wrappers, so you can do what I do, where you copy a pre-existing one and find and replace some names, and you've just made a commit to Lumen. And then you can say, I worked on a VM for a language, which is pretty cool. IList and calendar probably don't need any internal changes to the runtime, but all the other require fleshing out the type implementation to handle external types. Because we aren't doing distribution yet, all the external stuff like external PID, external reference, we held off doing for now. They exist, but in most of the cases, they end in an unimplemented macro, so you know to file a bug with us to like, hey, I actually want to use this. For the far future, maybe never milestone, because they are in the beam for debugging, like the Erlang docs literally say, this is for debugging, please don't use it. Or there may be older functions that are unused, or Lumen and the Lumen runtime can't return the same information because the BIF returns information specific to how the beam works, or those abilities are restricted in the WebAssembly environment. We may just not get to them. That being said, remember, I'm testing Lumen on x86-64, and I mentioned embedded. Lumen is targeting at WebAssembly now, but it doesn't just work there. So if you're like, I want to make this work on a microcontroller, I need this system interface, just tell us. We want Lumen and the Lumen runtime, even when deployed in WebAssembly, to be able to work with the Erlang and Elixir tools we've all come to expect. This includes distributed Erlang, Observer, and support in editors and IDEs. To interact with the Erlang and Elixir tools that exist on the host machines outside the browser, we'll need to implement distributed Erlang. One of the possible approaches is using the binary stream support in WebRTC, which would allow connections in either direction, and even allow browser tabs to become nodes in a mesh. For just connecting back to development boxes, though, we could use WebSockets. In either case, though, the host machine will have to implement an adapter so that it can bridge the WebRTC or WebSocket binary protocol and go to normal Erlang distribution if you want to have a mesh in normal nodes. But that's not that weird. Lots of people have written weird distributed Erlang to like work around issues on Heroku. For Observer, we'd like to use either the distribution transport to allow using the WX Windows GUI on the host. It should also be possible to potentially leverage the work of Square's WebObserver or Observer Live that just came out to have Observer inside the tab. The only downside we see with that is that it may not always work when you really want Observer to work because the tab may be under so much load or so janky that rendering inside the tab just doesn't work. If that's the case, we may go so far as to implement DevTools extensions in Chrome and Firefox, because those usually are more reliable even when the page is janked. For editors and IDEs, since I'm the developer of IntelliJ Elixir plugin, I plan to focus on JetBrains IDE integration. Sorry. This will include support for disassembling WASM files to the WASM text file or WAT, and decompiling to Erlang and Elixir if I can infer heuristics through the Lumen output, which will mostly depend on what LLVM does to your source. As we are passing through LLVM with link time optimization, this could be pretty difficult. Finally, once we have debugging in the browser, we may add a browser extension to link debugging steps, as happens right now with JetBrains RubyMine, when you can have an extension to step back and forth between your JavaScript code and your RubyMine code. The W3C community group for WebAssembly, which Paul and I are a member of, has a subgroup dedicated to debugging. Nick Fitzgerald from Mozilla has proposed a standard to allow WebAssembly modules to ship a debugging module that is specialized to their language. So that would get around the whole problem how, like, the debugging tools in Chrome and Firefox can show you JavaScript code, or it can sometimes show you a source map of your real code, but it can't syntax highlight that source code, and it definitely can't let you step in your original source code, and it definitely can't let you like evaluate variables in the original language. His proposal would allow that to happen, and so we're going to support him in his work to get that accepted, because we're not browser vendors, but we really like that tool. And now back to Brian.
So I know that we've gone over on time, so I'll be quick over these last set of slides. But I just want to talk about why we're doing this. We spent a lot of time hearing about the how we're implementing it. But for my own reasons why I'm dedicating a lot of Docker resources and money into this is like currently this is the known state of web development in Elixir. We have server-side render development. With Phoenix, we have the applications that you probably were making with jQuery a few years ago that then got rolled into more complex client-side application development, and you're like, why is it taking me a week to do something I used to do like an hour in jQuery? Now live view is helping save you from that quite a bit. At Dockyard, we do a lot of heavy client-side application development using Ember. The leaders in the space right now, though, we recognize are React, Vue, and Angular. But when we first started taking on building single-page applications, we were coming from Rails background. And the nice thing of that occurred within Rails, why a lot of people gravitated towards it at the time, was the value proposition that they put forth was you can build these applications in half the time, half the money, compared to doing it in something like Java back when Rails first came out. The sad reality that we soon came to realize of building out client-side applications in JavaScript was you can build the same applications in twice the time for twice the money. So it takes so long to build out these applications, then maintain them, and dealing with all the things that go wrong and trying to extend them out. It's very, very time consuming. So when I was kind of thinking about what justification we could have for Lumen, or wasn't even named Lumen at the time, just Elixir and WebAssembly, Jose impressed upon me that we have to start thinking about it from backwards. We have to start thinking about like where we want to be and working back from there. So I started looking into some pre-existing works, and it turns out that Joe Armstrong did some research in this space. He built out a GUI built in Erlang to communicate with X11, and he wrote a paper on it. So I want to read some quotes from it. Conventional programming languages are sequential. The widget libraries for GUI programming do virtually everything in terms of callback routines. So if a GUI system has to set up a number of callbacks in a number of different places, then if things start happening within a window, it becomes almost impossible to say what will happen. In the case where callback routines have to manipulate shared resources, this provides a fertile ground for errors to grow. This is about X11, but you could say the exact same thing about JavaScript. And just the nature of having to reason about concurrency in JavaScript. Dealing with callbacks and promises are just a nice way to flatten out your callback depth. They're not real, in my opinion, in my experience writing Elixir and over the past few years, it doesn't give me the same nuance in the way I like to now think about dealing with concurrency. The reason why GUI programming is difficult has to do with concurrency. GUIs are, by their nature, concurrent. Web applications are GUIs. We have asynchronous network requests happening. We have asynchronous events happening in the browser. So applying a language and a way of thinking that handles concurrency well only makes sense. Since Erlang is a concurrent programming language, it's natural to map each concurrent activity to a GUI onto a different Erlang process. Suddenly, the programming model becomes simple since there is no impedance mismatch between the concurrent structure of the GUI and the manner in which it is implemented. Another prior work, of course, is Scenic UI, which was presented here last year by Boyd. And some of the ways that I don't know if he tapped into Joe's paper or if he came up with the idea on it individually, but some of his implementation maps very well against what Joe was saying. So when I started thinking about this, I was thinking about like, how can we do this? Like, how can we make it a differentiating experience of building out web applications enough where it's going to make people want to write something in it? Even if Lumen ends up being faster than most other languages, other frameworks, what's the value of migrating your applications over to it? We need a order of magnitude kind of differentiator to draw people in. And I don't think rendering time is that anymore. Most frameworks are kind of like, they're margins of error away from each other in terms of rendering time. So we need a way to build out and reason how we're building these applications, which Elixir is perfect at. So we look at the DOM tree. It just happens to map perfectly against the supervisor tree. So what if we were able to actually map and have each node within a supervisor tree manage an element in the DOM? And I'm not suggesting that this is the long-term solution for a rendering engine, just that this is something that we can think about and apply now with Lumen. So I built out a little demo of this, and they're not the Erlang supervisors or Erlang workers, because in this theoretical prototype, the nature of the supervisors is we need to treat supervisors almost like workers, and we need the workers to act like supervisors. So I had to write out something custom on top of it. Oops. So I will show the demo of that real quick. And bear with us, because this is the first time I'm going to be running it. So we will see how it goes. Let's see here. OK, so what's happening right now is if I open up the console, we're going to see, Wait, OK, all right, things are happening. All right, so it's compiling in the browser. So this is what's happening right here. And we're seeing all of my supervisors going. And then what's actually happening is that it's going to pass in an AST of a parsed HTML template. And it walks the AST, and it's going to instantiate a supervisor and build out the children of that element. And then it actually associate and store the element reference in each supervisor. So it goes down, it walks it, builds it out, inserts the nodes into the DOM, and it renders it out. So this could be something that we build upon in terms of a rendering engine. I don't know. I know that the state of most other frameworks is iteration upon VDOM, but we have a different way to think about building out web applications now. And we haven't even gotten into event handling, right? So what I'd like to see is hopefully we get some people really thinking about this, good questions after the talk, and maybe even some participation on saying, I got a really good idea that we can take advantage of something in Lumen that we weren't previously able to really implement properly in the browser. All right, so areas of interest. Luke touched upon this a bit. We want to build teams around tooling to implement working with Observer. We want to integrate with the browser dev tools. We are very cognizant of the asset footprints that are going to be output. I know that this is usually a non-starter for some companies to adopt any type of web technologies. So What we were seeing right now is in the hundreds of kilobyte size, and we haven't even started to go down the road of any compiler optimizations or, as Paul was pointing out, dead code elimination. Luke spoke briefly about the networking. A nice thing that we can start to explore is actually, rather than having to do JSON serialization and deserialization in network requests, we can just emit Erlang terms, and we can skip that whole overhead of serialization. The compiler, we want to integrate with more tightly with Elixir's compiler. We want people that have experience or maybe connections with some of the browser vendors and may be interested in getting involved with some of the specifications for WASM and WASI. And finally, building on some stuff around the framework. So as we're closing up here, I just want to thank Paul and Luke, and where's Hans? Hans is over here. So Hans, he came, we hired him a few months ago. He had been writing an interpreter on his own independently. It was a huge piece that we needed, and so we hired him to come in, and his trip over the past 24 hours has been interesting. He flew from Denmark into LAX, 11-hour flight, and then got here, got bumped out of the hotel, came back the next day, and then the hotel lost power, and then it caught on fire. So he's, hopefully he has a bit of a smoother experience. So I just want to, point out that these guys really kicked ass to get this thing going. Like, even though I announced that this is what we were going to be doing last year at this time, work on this didn't really start until February. So this is really just a few months worth of work, and they've been really working overtime to get to the point that it currently is. So we're going to skip the questions, but I want to point out that the GitHub organization is Lumen, and it's currently private, but once I am able to get off stage, I'll open it up to the public, and everyone can start cloning and trying things out. So thank you very much, and I yield the time back to the conference.